Hello, my name is Chris Knight, and I am going to be demonstrating my Labview project for ENGR 267 Engineering Programming at OIT for Dr. Mateo Aboy and James Eastham. What this is a combination oscilloscope and waveform generator. First, we're going to look at the waveform generator. The functionality for it is located here on the right-hand side, and it does sine wave, square wave, triangle waves, sawtooth waves, and DC. We can change the frequency here. Let's actually look at something. All right, we can change the frequency up here. This is a frequency multiplier, so whatever this dial says, this will multiply that. On the bottom of the screen, we see what the voltage is, which is this amplitude. You can change that here. The frequency is shown here, and this is the period. For square waves, we can also adjust the duty cycle. This only exists for the square waves. We can adjust DC offset for any of the waves. We can add noise to any of the waves. Every time you change a button here, the screen is automatically readjusting in order to show approximately the same number of waveforms, regardless of what the frequency multiplier is set at. We can do uniform noise. This knob will adjust either uniform or Gaussian noise depending on which button is pressed. And that's basically it for the waveform generator. Oh, wait, we can change the intensity, which is basically just the line width here. This intensity is working for all of the screens. So we can change it in the oscilloscope screen as well, which makes it a little easier to see here. So basic oscilloscope functionality, we have 5 choices for our y-axis, or volts per division here. We've got 5 choices for our time axis. We can adjust the vertical position. We can press this little reset button and it'll put our vertical position back to where it was. We can trigger on either a falling edge or a rising edge. First, we're going to turn on this button, which is a frequency counter. It shows up on the top right-hand side here. When we turn on a triggering, we can set that triggering with this by dragging this cursor. So we'll set it right here, kind of at the top of that noise. Well, I guess it's too close to that noise. And it triggered again on some more noise. We have X and Y cursors. Our Y cursors allow us to take differential voltage measurements. And we have this, speaking about voltage measurements, we have a voltmeter that is another little draggable cursor. So we can say, well, where is the voltage of that one little tiny peak of noise right there? And we can pinpoint any part of the waveform to get a voltage at that particular point. We have X cursors, which gives us our time measurements. We can drag those out. And what else? Sine waves. Triggered. Triangle waves. Oh, wait a minute, run. Okay, triangle wave, triggered again. How about some uniform noise? Oh, it's not going to show up until we run it again. Yeah, apparently the uniform's noise isn't so high. We can move the DC offset. Okay. And it's going to run into the trigger. And bang, triggers. Sawtooth waves. Oh, I got to untrigger. Turn off the trigger. Okay. Turn back on the trigger. We'll trigger on the falling. I mean the rising edge. It's going to stay triggered. Yep. Now I'm higher. It's not going to do it. You can increase the amplitude and it triggers. Okay, we have these buttons which give us measurements, our minimum, our maximum, our mean, peak to peak, DC amplitude, and RMS. This will go up to 20,000, except for at 20,000, there's just not enough samples to really look very low. Well, kind of have to change this. Turn back on some triggering. And there's just not enough samples. I don't know if you can hear it through the speaker, but or the microphone, but my CPU is starting to go nuts right now. Go back down to a more reasonable frequency. Oh, we're triggered. Okay. Oh. What else? We have spectrum analyzer. So this is looking at uniform noise over the top of a sawtooth. We can look at Gaussian noise over the top of the sawtooth. And you stop triggering. Okay. Square wave, sine wave. No noise on a sine wave. We can change the intensity of that. Just line width. We can save to a file. That'll create a very large file on my disk. It's not very interesting to look at. And that's basically it. Looking at the program itself, on the left-hand side we have in a frame for sequential operation. This sets a bunch of initial parameters. All of this is using property nodes. Again, using property nodes, I'm changing the line width for all three graphs depending on where the tab is set. I've implemented the voltmeter using a little sub-VI. Volts per division, time division. These are the X and Y measurement cursors here. Again, mostly property nodes. Here is the frequency counter in the on-screen measurements. This little section right here is being shown on the waveform generator display, which is duplicating this information over there. Here we have on-screen measurements. These are the buttons here. And a little bit of error handling here to deal with an obnoxious error with the mean, where if there's not enough crossing of the baseline, it'll generate an error and crash everything. So this little VI right here says ignore the error, and this takes the cluster apart and sends the status of the error over to this case, which says if there's an error, put up a message on the screen that says increase the time division. Here is for writing to a file, vertical position, and then triggering, and some experimental stuff that I didn't implement. And there's the waveform generator here. The noise is being done separately from the waveforms, and then they're being mixed in this nested case statements here. All right, guess that is basically it. Thank you very much.